Pleasure to be invited to address the Sage Center. I hope I'll convince you that I am learning a certain amount about the psychology literature, which I found very interesting, but I don't get a lot of opportunities to present my work to psychologists, and so I'm very much looking forward to learn reactions. People who I'm sure know more than me about at least certain aspects of things I'm going to be talking about. So the main argument that I'm trying to make is that economists need to learn more about the psychology literature, and a particular aspect of it, which is to learn more about the nature of imprecision in people's construal of the objective situation that they're in as a foundation for decision making. The aspect of that I'm going to talk about in particular today is things we know about number representation in the brain and the evidence for what is often called an approximate number system. And the basis for believing that there is an approximate number system in the brain is based in particular on the observation that people, and at least some other animals, have an observed capacity to make quick judgments about how many items are in a group, not through an algorithm that involves explicitly counting the items or necessarily using number names or reasoning about arithmetic, but forming an impression of groups of items that contain a larger number or a smaller number. This is a capacity that seems to develop earlier than language, and it's a capacity that is demonstrated to exist in people growing up in remote tribes that don't even have a lot of number words in their language, and nonetheless can make approximate judgments about quantities of items. These judgments of numerosity of a display of items are well known, and this has been studied since the 19th century at least, are only approximate judgments, at least when there are more than maybe 4 or so items. For a very small number of items, it seems that we have an ability to recognize patterns, pattern of 2 items or a pattern of 3 items, and automatically recognize as a triple. But once it gets to be more items, it seems it's a different mental faculty that's involved, a faculty of estimation, and that this produces only an approximate judgment of a larger or smaller quantity. And this nature of the approximate judgment of numerosity seems to have a lot in common in its structure with judgments about what I'll call extensive sensory magnitudes. So things like lengths or areas or acuteness or number of angles, all cases where judgments about something being more or less on some dimension are made, and are made in a way that doesn't have to involve quantifying those things. Stanislas Dehaene has written a well-known book about this literature called The Number Sense, and he calls this capacity a number sense. The sense of the size of numbers that seems to have a lot of similarity to other senses, sensory perception in other aspects of these lives. So what are some important behavioral signatures of drawing on this approximate number system, which are of interest to me because I'm interested in what kind of structure of imprecision it has that might be relevant then to economic decisions if this system is being drawn on in economic decision making. The one basic thing that's observed about it is that the recognition that one number of items is bigger than another is imperfect, so mistakes are made in the judgments that are made about that, but the accuracy is increasing in the distance between the 2 numbers. The difference in the number of items in 2 arrays is sufficiently different than judgments about which one has more items in it become quite accurate. The closer the 2 true numbers are to each other, the greater number of mistakes. And so one can graph what's called a psychometric function, graphing the probability, say, of judging that a second cloud of dots has more dots in it than a first cloud of dots, varying the number of dots in the second cloud, and see how that gradually and monotonically, that probability of response varies with the objective truth. This is an example of psychometric functions for numerosity. So what's being done here in each of these three panels is there's some reference figure. The reference figure has 25 x's in it. It's x's rather than dots in this particular experiment. 100 x's are the reference figure here. 400 x's are the reference figure here. And in each case, one is asking what's the probability that the subject judges a second array has more x's in it than the first array as a function of what the number of x's are in the second array. And so what one is observing is that the responses are probabilistic. What's on the vertical axis in each case is the probability of judging that the second array has more things in it, with that probability being converted into a z-score, so that exactly 50% probability of judging one thing as opposed to the other is being rated as 0. And the probability is monotonically increasing in the extent to which the second array really does have more items in it than the first array. Another characteristic that's observed is that the distance between two objective numbers of items in arrays that are required for a given degree of accuracy of discriminating which of them has more things than the other gets larger when the numbers themselves are larger, and it's often argued that it's essentially the percentage difference in the number of items in the two arrays that matter for the probability of judging that the second one has more items in it than the first. And so it's said that something like Weber's law, which was of course discovered in other sensory contexts for things like comparisons of lengths, also seems to apply here to comparisons of numerosity. Here's an example of some data illustrating what I mean. This is a task where two clouds of dots, first one cloud of dot is presented, it goes away, a second cloud of dots is presented, and the subject has to say whether they think the second cloud of dots have the same number of dots in it as the first cloud. The experimental protocol is one where exactly 50% of the time the second cloud does have the same number. So just blindly guessing, there's no reason to do better by guessing that it's the same or guessing that it's different. What's being plotted here, each of the curves with a color, the color is determined by what the number of dots really are, or sorry, what the number of dots were that were presented first, the reference. And then on the horizontal axis is the number of dots in the array that's presented second, and the vertical axis is what fraction of the time the subject judges that the second array has the same number of items in it as the first array. Each of these curves peak when the items in the second array really are the same. So this green curve is when 30 were the number in the first array, and its peak is when 30 is the number of items in the second array. But one observes some probability of judging that they're the same when there are really 34 or 36 or 38 in the second array, even though the first array 30 in it. And the thing I wanted to point out is not just, well, there are mistakes, and the mistakes are more likely when the difference between the number of items in the two arrays is not too different, but these curves also get wider as we go to the right, as we increase the number of items in the first array. So if there were only 6 items in the first array, then there's a non-trivial probability of judging that it's the same number when, say, there are 8 items in the second array. But if it's more than 8 in the second array, it's not too likely that you judge it's the same number as the first array that had 6 items. When we go from 6 items to 30 items, now we have a much wider curve there. And the claim is that the probability of thinking that the second array, judging the second array is the same number of items as the first array, when the first array had 30, an increase from 30 to 40 lowers the probability by about the same as an increase from 6 to 8 lowers the probability of thinking they're the same over here. So that's a Weber's law-like relationship for discriminability of numerosities. Then there are experiments that have people produce estimates of the number of items that were displayed, either visually or maybe orally. And these estimates are variable for a given stimulus. It's just that there's some perception, which is a function of what was presented, and the perception is maybe different from the truth, but it's always the same thing. Reported estimates are variable for a given stimulus. They're more variable when the number of items is larger. And in fact, a quantitative regularity that's often been reported in the literature, something called scalar variability, is the proposition that the standard deviation of people's estimates of the number of things they were shown grows in proportion to their mean estimate of the number of things that were shown. So an example of this relationship, this is from a study that actually involved presenting things orally, a series of clicks, and you hear a certain number of things, and then you have to produce a series yourself that you think had the same number as the number of things that were presented. And so what's being graphed here as a function for each subject, as a function of the number of things presented, the truth, there's a graph of both the average number in the response of the subject and the standard deviation. Squares are the mean of the subject's response, the circles are the standard deviation of the subject's response. And what one is seeing is that the standard deviation and the mean are pretty much growing together as one increases the true number of items, and that's this proposition of what's called scalar variability. Okay. What kind of model of the nature of the underlying imprecision in the internal representation does this suggest? An idea that has been popular in the literature on representations of numerosity is that the mental representation of a given number of items can be thought of as a noisy readout of the position of that number on what's hypothesized to be a logarithmically compressed mental number line. So the idea is that the degree to which one might confuse one number of items with another number of items depends on how close they are in psychological space, and the mapping of the objective number into the location on this mental number line is not a linear relationship, but a logarithmic relationship. So how different the true numbers are in their logarithms, which means their percentage difference, is what determines how easily confusable they are on the basis of the mental representation. So one way of capturing that mathematically is to suppose the mental representation can be summarized by a single number that's bigger or smaller when things are perceived to be more or less, but that this number is a draw from a probability distribution conditional on the true numerosity. And one simple model would be that this statistic R is a draw from a normal distribution with a variance that's the same regardless of what stimulus that was presented, but the mean of which is growing with the logarithm of the true numerosity. So that would capture this idea of logarithmic compression on this mental number line, which is the mean of then this retrieved value the judgment of numerosity is going to be based on. Okay, and so that could, for example, explain why you would observe Taylor's law type relationship. So the question I want to ask though about this is, does it have any plausible connection to decision-making in economics? And you might easily think not, because those examples I was giving was about the errors in people's judgment about the number of things in some array, something they could see, say, in their environment. And you might say, well, there are occasionally economic decisions where it matters whether you can accurately judge how many things you're being offered. You're going to buy a bunch of bananas, and you have a sense of whether there are a lot of bananas or only a few bananas in the bunch that you're buying, and that's relevant. And so how good your vision is at quickly sizing up numerosity maybe is relevant for a decision like that. But you say that's a small part of economic life, that aspect of visual acuity is really going to be important. In lots of economic decisions, the relevant quantities are going to be indicated to people using number symbols or number words, and the whole reason why we in our societies have invented number systems, and we drill kids so much on learning to use numbers is because then once you learn to use numbers to communicate about quantities, they have very precise meanings, and if we assume people economic decisions have that down, they understand the meanings of numbers. It's taken this issue of imprecise repetition, numerosity of things off the table. But in fact, there is evidence indicating that these same imprecise representations of number in the brain are being activated not only when some number of items is displayed, say visually by a cloud of dots or something of that kind, but when the numbers are presented symbolically using a number word or Arabic numerals. This paper I referred to by Piazza and co-authors is an example of one of a number of studies showing that the same part of the brain, a region in the intraparietal sulcus that's thought to be where these number representations reside, are not only activated by people seeing particular voxels have more activity in them when, say, 7 items are shown in a visual array, but being told the number 7 with a word or with symbols produces a very similar pattern of activation as seeing things in an array. So that suggests that even when people are processing the information conveyed by these number symbols, that among the things that happen in the brain are calling up a semantic representation of how large or small that number is that's using the same mental faculty as is involved in numerosity judgments. Now, saying this doesn't mean that I'm proposing that humans can only make use of these fuzzy semantic representations of how big or small numbers are in making decisions. We know that people who've gone to school and made to spend years studying arithmetic can manipulate symbolic representations, and they use rules that they were drilled on in school. What I would claim is that even once people have learned to do this, it's not the only thing they do in life. And in fact, I think these approximate number system representations are also available. They're called up when you're told about numbers. They can in fact be accessed more quickly and with less effort than things you know propositionally about the meaning of number symbols and things you would do with them. And I think that this is particularly likely to be drawn on, for example, when a response has to be given quickly. And so there are experiments where people respond to numbers that are presented, say using a symbol, a 2-digit number on the screen with Arabic numerals, but requiring a quick response. It seems that it's this semantic representation of the size of the number that's drawn on, or if a response has to be based on memory of numerical information they were told sometime in the past, it also seems that calling up the semantic representation of that number is more likely to be available than exact symbol that you were told about the number. So an example of this second claim is an interesting study by Dehane and Marcus. I think it's pretty interesting for the idea that this might be relevant to economics. They study the accuracy of people's recall of information that they were given about the prices of particular items. So they've been told a bunch of prices, and then after a time delay, they have to try to say what they think the prices of the things were. People make mistakes. The interesting thing is, what's the structure of the mistakes? They find that this property of scalar variability applies to the mistakes in people's recall of prices. So if you graph the average price estimated by the subjects for the items, different items are these different dots on the horizontal axis, and the standard deviation of the estimates of the price of that item on the vertical axis, you find something pretty close to, this is a log-log plot, pretty close to a linear relationship with a slope of 1 when you plot it as a log-log plot. So this scalar variability that shows up as a irregularity about the structure of errors when the approximate number system is used to make judgments about the number of things presented visually is showing up here, even in a case where the information was presented symbolically. They were told prices saying it's 15 euros and 98 euro cents or something. And they're also producing their estimates using number symbols. They're being asked, what do you think was the price? And they're using number words to describe the prices, but we're seeing the same kind of structure. So what I want to further hypothesize is I think that there's reason to suspect that people also rely on these approximate number system representations in economic decisions when the decision is one that requires them to compare the sizes of two or more numbers. So it's not just going to be a question, I can give you $10 or I can give you $9, which would you like better? That just requires that you remember, you learned to count. You remember 10 came after 9, okay. As long as you recognize that, then you don't, there's not going to be error about whether you'd rather have $10 or $9. But if you have to make a decision about things that are described using numbers, but there is some integration of the sizes of two or more numbers that's going to be required, that may point you in different directions. Some numbers make one option more attractive, other numbers make some other option more attractive. And furthermore, when it's a case when the decision maker doesn't consciously resort to an arithmetic calculation to decide how to manage this trade-off. Now, in economics, certainly we teach classes where we drill people on ways particular types of economic decisions might be made in a very principled way, doing calculations, and we drill people at how to do various kinds of calculations. You calculate the present value of an investment and so on using formulas. We know it takes some work to teach people to do those things, that even when they're, pretty highly educated people and they get to college, it doesn't mean that they just know those things and it's obvious, And so in ordinary life, I think people often don't consciously resort to applying some formula and using their very precise knowledge of the meaning of number symbols in some precise calculation. They're instead able to make decisions, forming judgments about how big the different numbers are that they've been told that are then influencing the decision. But I think it's reasonable to think that what's drawn on in that case, when they're forming an intuitive judgment about whether the on balance, one option or another, looks more valuable to them, is it's this semantic representation of the size of numbers that's going to be drawn on. And so understanding the structure of the imprecision in that representation may be relevant to economic decision making. So the kind of case where this comes up that I'm going to talk about extensively in the talk is specifically laboratory experiments in which a subject has to choose between simple gambles that involve different amounts of money that you might get with different probabilities. Both the potential payoffs and these probabilities are stated by the experimenter using number words. But what one observes is that when the same choice problem is repeated multiple times, the choices appear to be random. The same decision maker presented with exactly the same choice will not always make the same decision. On the other hand, you can try by repeating the choice problem to collect evidence on the probability of one response or another and find that the probabilities seem to vary systematically with the properties of the gambles that are being offered. So this is an example of this from one of the earliest papers, experimental papers in the economics literature, published in the Journal of Political Economy back in 1951. Probably some psychologists at least will recognize Mosteller's name as a well-known mathematical psychologist who was dipping into economics on this particular occasion. So what's going on in the figure is this is all data for one subject. Over the course of the experiment, the subject has made repeated decisions that were presented in the same way. In each case, the question is, you can choose to pay 5 cents to take a gamble. If you pay the 5 cents to take a gamble, you'll get a certain amount of money. If a coin toss comes out one way, nothing. If it comes out the other way, the amount you can get is different on different trials. And that's what's on the horizontal axis, is what the amount is you would get if the gamble pays off. What's being plotted is the fraction of the time that the subject decides to take the offer or not as a function of what the amount was that the gamble would pay off. And what you see here is that if the gamble is good enough, it starts becoming a high probability of them taking it. If it was as much as 16 cents, they took it on all the occasions, I think 14 times it was offered, and they always took it. If it's bad enough, they also never take it. But in the middle, some of the times the subject took the gamble, some of the times it didn't, even though it was exactly the same decision problem on those multiple times. Furthermore, there does seem to be regularity, though, in the probability. So the probability is monotonically increasing. The more favorable the gamble is, the larger the fraction of the times the subject takes it. And that, I hope, reminds you of the psychometric functions I was showing, for example, for comparisons of numerosity. A similar sort of phenomenon seems to occur here. And of course, our authors, being familiar with the experimental psychology literature and psychophysics, the fact that they plot data this way and plot a psychometric function isn't an accident. What they're doing, why it's published in the Journal of Political Economy, the figure, is it's showing how they were using the raw experimental data to extract something that the economic theory is going to be asked to explain. They're using the raw data to infer an indifference point, to ask how good did the gamble have to be to get the subject to exactly be indifferent between taking it and not, as measured by exactly a 50% probability of accepting it. They call that the indifference point. They want the von Neumann-Morgenstern utility function of the subject to then explain why, for that subject, the indifference point is right there. For people who know the von Neumann-Morgenstern expected utility theory, doesn't matter if you don't, but that's the object of the data we're going to be used to explain. The part about the randomness was not going to be explained by the model, but the authors, wanting to explain their method, how did they measure the indifference point that the theory has to explain, they talk about, in fact, the psychometric function that they've had to interpolate to find it. Okay, so what's going on there? The fact that you have a graph like that is something that makes sense if you think that the subject's judgment on each of the times they're presented with the choice about whether the gamble is worth taking or not is based on imprecise semantic representations of these numbers that were specifying the amount of money. So there was an amount of money that the gamble would pay off if you get the good outcome, and there was also an amount of money you had to pay in order to take the gamble. And I'm going to hypothesize that they're basing the decision of whether the one amount is big enough to be the gamble to be worth taking, given the cost, which is that other amount, is going to be based on imprecise semantic representations. If that's true, then you should expect random trial-to-trial variation in the choice, at least when the decision is a close enough call, just as with those psychometric functions for comparisons of numerosity. And I want to note that this is something you should expect to occur even if the decision maker's decision rule, what they're doing based on the mental representation of the numbers they were told, is an optimal rule conditional on it having to be based on those noisy representations. So once you are willing to say they must be drawing on noisy semantic representations of how big the numbers are, then even the best possible rule for using that information is going to have the property that it should generate a psychometric function of the kind that we see. And something I'm interested in pursuing is, in fact, asking what we would expect data to look like if we think that the uses that people make of these noisy representations is pretty good, is pretty well adapted to the kind of decision problem it's being used in. But I'm interested in the kind of errors that are produced by the nature of the imprecision in the number representations. Okay, so what's interesting about that is an explanation of the figure. So it can explain why there is randomness in the observed decisions, which is itself something that, say, the von Neumann-Morgenstern theory of expected utility maximization didn't give you any reason to think should be there, although obviously our investigators were expecting it and they graphed a psychometric function. They asked the same subject many times the same question. Why? Why did they bother asking it, 14 times the same choice? Because they were expecting randomness in the decision and thought you'd need to try and measure the probability of responses rather than just asking which one that they like better. But another thing that it can explain is the existence of departures from risk neutrality.
So this, and that can be attributed to the same source, namely that the subject's decision has to be based on this approximate number system representation of the payoffs. So this absence of risk neutrality is itself something kind of puzzling. In the case that I showed you, the subject appears to be somewhat risk averse, by which I mean that they decline the gamble more often than not when it's a mathematically fair bet. And it has to be better than a mathematically fair bet for them to appear to be indifference between taking it and not taking it. Here's the indifference point. It's a mathematically fair bet if 10 cents is what you would get if it pays off, right? Because you pay 5 cents to take the gamble, you have a 50% chance of getting the outcome. So in expected value, you get something worth 5 cents if you take it if we were here. But when we're there, it's a mathematically fair bet. They only take it 4 times out of 14. More often, not 10 times out of 14, they don't take it. It has to be better than a fair bet to get them to take it as often as they don't take it. Okay, so we call that risk neutrality. What's the puzzle? Economists aren't fazed by that, of course. But the standard explanation for risk aversion is representing a rational choice, and this is an idea that goes back to Bernoulli's work back in the 18th century. He proposed diminishing marginal utility of wealth as the reason why people would make risk-averse decisions. That's not especially plausible in the example I was showing you, because to explain why the indifference point was to the right of 10 cents to the extent that it was, I have to assume that the diminishing marginal utility of wealth for this subject diminishes really fast when I increase their wealth by just a few cents, right? Because that figure said that even if the amount the gamble would pay off is 10.5 cents at the time, that they are more likely to turn it down than to take it. So the diminishing marginal utility of wealth can explain that. It can explain it if it says that increasing your wealth by 5.5 cents, which is what happens if you took the gamble and it pays off, increase your wealth by 5.5 cents net, that does not increase your utility as much as your utility would go down if you lost 5 cents because you paid 5 cents and it didn't pay off. You say, is that possible? Sure, that's possible, diminishing marginal utility, but it means diminishing marginal utility is very fast, right? And if I believe that it diminishes that fast, that applies now that for larger gambles, we should observe extreme caution about willing to take bets, which we don't see. People do invest in things that are not the absolutely safest possible financial asset when there's sufficient average returns enough to make it tempting. So that's in fact not a very plausible explanation of the kind of risk aversion observed in the case of very small gambles like this. On the other hand, if we hypothesize that the subject's decision is based on these approximate number system representations of the monetary amounts, then we shouldn't really assume that the average assessed value of a gamble should be a linear function of the payoff specified. Why not? Well, what do we know, again, about accuracy of judgments of numerosity? We have these experiments where subjects produce an estimate of the number of things in a visual array that's presented to them. I said there's random variation in their responses, but there's not just random variation. On average, the response is not the correct number. There are systematic biases in the responses. And if I ask what's the average response, this N hat is the subject's estimate of numerosity, the average response, conditional on the true numerosity being N, plot that as a function of N, it's an increasing function of the true number, but it's a concave. It goes up, but it's bending. It's becoming flatter as it gets higher as a function of N. That implies that the number is increasingly underestimated as the true number is larger, increasingly underestimated even in percentage terms. And on the other hand, it's often overestimated when the true number is a small number. The crossover point between overestimation and underestimation is also variable across experiments. It's higher the larger the average value of the numbers used in the experiment. That's something that's sometimes called the central tendency of judgment, well documented in other sensory contexts. One finds it in these estimates of numerosity as well. This is an example. Oh, sorry, make that come back. Okay, there it is. This is an example of a study that involves presenting people with clouds of dots with different numbers of items in them. They're moving a slider to produce their estimate of the number of items in the visual array. What's being plotted is the distribution of responses as a function of the number of dots in the array that's presented. And what you see is that on average, the response is an increasing but concave function of the actual number of dots. There's overestimation on average for smaller numbers of dots, underestimation on average, though, for larger number of dots. The point of crossover is different in the two experiments that differ only in the range of numbers presented. Here, they're always between 1 and 30 items. Here, it's between 1 and 100 items. Same kind of visual figures are used to present, say, 20 items in the two cases. But whereas 20 items is already enough to be in the range where it's big enough that there's underestimation on average most of the time of the number of items presented. In this context, 20 is significant overestimation of the number of items. And so that's the central tendency of judgment showing up, that the crossover point is shifting depending on what the average number of items are that are being presented. Okay, so one expects errors of that kind in judgments about how big numbers are when the estimate of how big the number really was is based on this noisy approximate number system representation, then we should expect biases in assessments of how big numbers are that have that kind of shape that would then easily produce the risk aversion that I'm referring to. As a model that can explain what's going on with the biases, why the biases are not such a strange sort of artifact. If you believe the things I said before about the logarithmically compressed number line, in fact, you should expect biases in numerosity estimation of the kind that I was just showing you. Suppose we're going to base the estimate of numerosity on this internal representation R. It's drawn from a distribution with the mean that's growing in proportion to the logarithm of the number. What would the optimal estimate of n be? Optimal is going to depend on what we're trying to minimize and in what distribution of possible situations. Suppose, say, the rule for estimating numerosity is going to minimize mean squared error of the estimate. Suppose you mean for it to be optimally adapted to the class of decision problems. It's going to have to be estimating mean squared error over some distribution of problems. If I suppose the distribution of problems is one where the true number of dots is drawn from a log normal distribution, then I can work out what the posterior distribution is for the true number, conditional on the internal representation. That's also going to be a log normal distribution conditional on the representation R. I can ask what's its posterior mean. That's the estimating rule that minimizes the mean squared error of the estimate. And it's going to imply that the subject estimate n hat should be a function of the noisy representation R of this kind. And there's a crucial parameter here, gamma, that determines the sensitivity of the log of the estimate to this noisy representation, which is on average equal to the log of the true value. That gamma is a positive quantity less than 1, depends on the ratio of the prior uncertainty, the sigma squared, to the amount of noise in the approximate number system. That's this mu squared parameter. The reason I wanted to point to that is we want to know how this is going to change. If something changes the amount of noise in the internal representation, increasing the noise of the internal representation, the mu squared should make this gamma further from 1, make it smaller, much less than 1, and that's going to affect the concavity of that relationship. So what that model is going to imply is that for any given true stimulus n is the true number of items presented, there should be a log normal distribution of the subject's estimates, n hat, and its mean as a function of n should grow as n to the power gamma. And I showed you where the gamma came in. Also, the standard deviation of the subject's estimates, conditional on the true number, should also grow in proportion to n to the power gamma, which means that's a model that implies you should expect scalar variability. You should expect the standard deviation of responses to be growing at the same rate as the mean response. It predicts overestimation for all small enough numbers and underestimation for all larger numbers. You can calculate where the predicted crossover point should be, and it's going to be proportional to the this n bar is the prior mean for n under that long normal prior. So if I change the mu, keeping these noise parameters the same, then crossover point n star should change in exact proportion to the change in that environment if the mean number actually presented. So you should expect a central tendency of judgment. Okay, so how am I going to apply this now to the subject's problem in that experiment? Consider a decision maker that has to choose between two options. One is risky, one is not risky. The risky option A, it's a gamble that pays some amount X with probability 1/2. The other option, the safe option, gives them some amount C for sure. Suppose their choice has to be based on approximate number system representations of these two numbers, X and C. And those are going to be different on different trials. So then if we ask what would be an optimal decision rule, taking as inputs these imprecise representations of X and C rather than their exact values, optimal rule in the sense of maximizing the decision maker's average financial wealth would be a rule that leads them to feel the gamble is worth taking when their noisy internal representations Rx and Rc are such that 1/2 times the conditional expectation of X, conditional on its internal representation, is bigger than the conditional expectation of C, conditional on its internal representation. Those two things, if these things have the structure of estimates in the approximate number system, these things are things that are random, conditional on the true X, random, conditional on the true C, but on average, this is an increasing function of the true X. This is an increasing and concave function of the true C, and that concavity is going to lead to non-risk averse behavior. So the subject should appear risk averse if they're using a decision rule like that, if when it's true that X is actually twice C, so X is 10 cents, C is 5 cents, that in a case like that, the conditional expectation of X conditional on its noisy representation is not as big as 2 times the conditional expectation of C based on its noisy representation. If that inequality holds more than half the time, it's self-probabilistic, random, this is random, conditional on the true X and the C, but if more than half the time the inequality goes that way, you should observe what I was calling risk-averse behavior, the thing that Stoller and Noji were documenting. And that's something that can easily happen in the model of noisy internal representations. In particular, if the two quantities X and C are being represented with the same degree of imprecision, so this logarithmic Cody model is determining the noisy representation of each of them, the new parameter is the same for the internal representation of X and the internal representation of C. And I suppose that the decision maker's decision rule is optimized for an environment in which X and C are both drawn from a log normal distribution, and under the prior, they're in fact both drawn from the same log normal distribution. Then I can work out what's the distribution of estimates of the percentage difference between estimated X and estimated C, and compare that to the actual percentage difference between X and C, and get a negative bias if the mean of this distribution is negative, which is going to be true if gamma is less than 1, and I showed you that gamma has to be less than 1, and if X is something bigger than C, which it is when, say, X is 2 times C, that logarithm is also positive. So it is going to be a model that fits quantitatively the kind of thing that's well documented in the numerosity studies if it was the basis for decision making in a situation like the Mosteller and Noji experiment. You should expect that departure from neutrality direction they saw. Not only can the model, though, explain why you would see small stakes risk aversion in a case like Mosteller and Noji, but it would imply that you would expect the modal choice to be risk seeking if I kept the same numbers in the problem, but made it a problem about random loss versus a certain loss rather than a random gain. And a certain gain that kind of change in the sign of risk attitude when you flip from gains to losses is something Kahneman and Tversky document in their famous paper on prospect theory. They call that a reflection effect. And they present a good deal of evidence for it. This model would make you expect that. It's a puzzle, of course, for the Bernoulli explanation of risk aversion. You have diminishing marginal utility of wealth, big enough to predict risk aversion for the small gambles involving gains. You should also see risk aversion for small gambles involving small losses, which is not what we see. In this model, this same condition, that this conditional expectation is less than 2 times this other conditional expectation more than half the time, when X is 2 times C, that same condition is what will imply the risk-averse behavior in the gains case and risk-seeking behavior in the loss case. And so the same model of imprecise representation of the numbers 10 and 5, if it delivers risk aversion in the one case, it should imply you would expect risk-seeking in the other case. Maybe I'll this and go on questions. Which is, okay, so it can explain some things, but you might say, do we need such a theory? Prospect theory also gives a descriptive account of exactly all of the phenomena that I was mentioning, and some that I've just skipped over. But anyway, the ones I just told you about risk aversion in the one case, flipping into risk seeking. In the other case, prospect theory says that you should expect that. It says that people make choices not based on what the distribution of final wealth is that they can get in absolute terms, but that they evaluate these different possible levels of wealth relative to a reference point. Let's say the reference point is determined by what you have at the time you're choosing between A and B. And furthermore, the value of gains from above the reference point is assumed to be concave. The value associated with losses relative to the reference point are instead convex. Okay, and so one part of the curve is concave, another part is convex. You get the things I was saying. So you might say, what's added by proposing that these things result from people basing their decisions on our number system representations? Why don't I just say there are irregularities? They can be summarized by prospect theory if the value function has a certain kind of shape. The reference point is determined in a certain way. And so one answer that I want to talk about is that we can explain why experimental manipulations that we would expect should change the precision of number representation, in fact, have an effect on choices. They can affect both how consistently subjects make the same choice across trials. They can also affect the size of subjects' observed bias for or against risk taking, whereas these manipulations are not things that should obviously be relevant to people's genuine preferences between the outcome of a gamble and a certain amount. So I want to illustrate some examples of such manipulations. So one simple idea, Miguel Barreto Garcia and his co-authors at the University of Zurich did experiments where they compare 2 different treatments. These are both experiments that involve subjects choosing between a simple gamble that offers some amount X with probability P, or they can have a certain amount C. Probability P is the same across all the trials. The X and C are different values on different trials. With 2 different treatments, the same kind of problems of that form are going to be presented to the same subject in the 2 different treatments. But in one, the numbers X and C are presented with number symbols. In the other one, they're displayed visually. Sorry, this is a mistake. It should say they're clouds of what are represented as 1 Swiss franc coins. And so 14 francs is represented by an irregular cloud that has 14 coins depicted. 28 francs is instead a cloud with 28 coins represented in it. And so they're going to be told what X and C are by these visual arrays of coins. That's the amount of money that you're giving up or that you're getting if the gamble pays off. Okay, what do they find when the number information is presented in the 2 different ways? They find similar psychometric functions for the subject's choices in the 2 cases, but that presenting the numbers visually rather than with the symbols results in a flatter psychometric function and a shift in the intercept. The flatter psychometric function is what the theory I just presented would imply should happen if the fact that the psychometric function doesn't jump up from 0 probability to 1 probability 1 at some well-defined indifference point. It's flatter because of the noise in the internal representations. If presenting the numbers visually results in more noise in the internal representation, then you should expect a flatter psychometric function. Even more interestingly, the intercept, the point at how good the gamble has to be to get apparent indifference to occur, that shifts in the direction of apparently greater risk aversion when the gambles are being presented with the visual image rather than being told number symbols. That makes sense under my interpretation of where the apparent risk aversion comes from as a bias that makes sense when the decision is being based on a noisy representation of a number. So the bias gets stronger when there's more noise in the representation of the number. It's quite puzzling if you think people have decisions that are responses to precisely understood quantities they're getting, and they're doing something. It's not risk neutral. It's the things that are, say, postulated in prospect theory, but we're taking the functions of precise awareness of what we're choosing. We don't see why these things change. So this is what the psychometric functions look like. We're superimposing psychometric functions for several different values of C. The different colors are the different values of C. On the horizontal axis is the ratio of X to C. And as X gets bigger relative to C, you're getting the probability of taking the risky gamble increasing. Solid line here is at the ratio of X to C that makes it a mathematically fair bet. So the probability is 55% here. So it's not 2, it's X over C a little bigger than 1.8, makes it a mathematically fair bet. That's where the indifference point would be for risk neutral decision makers. And what you're seeing is this curve is flatter. This is when it presented as clouds of Swiss franc coins. This is when you're told the numbers using Arabic numerals. The psychometric function gets flatter, but also this inferred indifference point moves further to the right. So there's greater apparent risk aversion in the case of this non-symbolic presentation. The payoffs, that's, I think, what you would find natural under the proposed interpretation of the departure from risk neutrality is resulting from drawing on prospect number system representation. It's mysterious if you think it's about people's preferences that determine risk neutrality. How does the theory explain it? That's why I told you about what this gamma factor was determined by. Gamma was an increasing function of the ratio of nu to sigma. If presenting the number information in the visual form rather than the symbolic form makes the nu and its internal representation larger, more noise in the internal representation, larger nu should make lower precision internal representation should make the predicted gamma further below 1. And that fact of gamma being below 1, the 1 minus gamma was one of the factors that was determining the size of the bias of the departure from risk neutrality. You should also get noisier choice from larger noise. Okay, a second example is the effect of time delays between when the information is presented and when the choice is made. So Hilde Hollander and co-authors, the same group, this is out of Christian Ruff's lab in the University of Zurich, both of its studies. It's a more recent study with Gilles as the lead author. They use a variant on this setup where, again, people are choosing between the same kind of simple gamble and safe options. In the main experiment that they discuss in this paper, both the gamble and the safe options are presented visually. There are these clouds of Swiss franc coins again. But now the two options are presented sequentially rather than simultaneously. So instead of them both being on the screen, the X and the C are both on the screen, and you're told to choose between the gamble and the safe outcome. One is going to be presented first. It's going to go away. There's going to be a time lag. Then you'll be presented the second option, and you'll only make your choice after the second option is presented. So the terms of the first option have to be retained in working memory until the choice is made. The hypothesis that they're interested in is that the terms of that option presented first are going to be represented with less precision than the terms of the second option because it has to be held longer in working memory. The reason they're using the visual array rather than the number symbol is that they expect that this effect of the time delay on the precision of with which something can be held in working memory to be greater when the thing that has to be held in working memory is a visual image rather than a symbol. And in fact, they do the experiment both ways. They get the stronger effect when the information is presented as visual images. And what they want to compare is the choices that the subject makes when the risky option is presented first to the choices that their subjects make when the same exact decision problems are presented, but with the safe option presented first, the risky option. Okay, so this is what their psychometric functions look like. They've separated problems where the stakes are smaller, stakes are in a medium range, stakes are in a larger range as three separate psychometric functions instead of superimposing them like in Miguel's figures that I just showed you. In each of these panels, there are two psychometric functions. The horizontal axis is, again, the ratio of X to C. On the horizontal axis, probability of taking the risky choice. On the vertical axis, the two different colors are what the psychometric function looks like in the case where the safe asset is presented first. That's the blue data. And in the case where the risky option is presented first and therefore has to be held in working memory longer, that's the orange data. And what you see is that when the numbers are relatively small for X and C, presenting the risky option first increases risk taking. The indifference point is actually moved to the left of this vertical dashed line is when it's a mathematically fair bet. So you actually see some bias toward risk seeking in those choices. In the case of the largest numbers, you instead see further movement to risk aversion by presenting the risky option first relative to the safe option first. Okay, so it's not clear why that should affect people's genuine preferences about these things. You're presenting exactly the same information, just presenting it in different ways, but the results are consistent with the prediction that increased time delay between the time of presentation and the time of decision should be expected to reduce the precision of the representation of the payoff in the case of the option that's presented first. What should that do under the theory I was presenting? You should expect the central tendency bias in the estimate of how big the number is to be stronger in the case of the option that was presented first. And what does that stronger central tendency bias mean? Stronger for the option presented first. If the risky option is presented first, it means that the value of the X, what you get if the gamble pays off, is perceived in a more biased way, which means a greater degree of overestimation of the risky payoff on trials where the risky payoff is small, but also greater underestimation of the risky payoff on trials where the risky payoff is large. So what that'll do is make the subjects more likely to take the risky choice when the payoffs are small, but also less likely to take the choice when the risky payoffs are large. And that's exactly what we observed. We observed a change in apparent risk attitudes, and it was different. The sign changed between the trials that involved a given ratio of X to C, where both X and C are small, or that ratio of X to C, but X and C both being larger than average values. So that also is a pattern that makes sense from the point of view of the theory. I think I am out of time, but I've been doing work on, other people have done work on the effects of changing the range of numbers that the X and C are drawn from and showing that that shifts these psychometric functions as well. Paper by Lawrence Friedman, or sorry, Kerry Friedman and Lawrence Gian, showing the psychometric function is different for exactly the same set of decision problems when the X and C are drawn from a wider range or from a narrower range, although the data here are for the same exact set of decision problems. With Arthur Pratt Caravan, I've been doing recent work looking at this same issue on the accuracy of estimates of numerosity when the number of items in a cloud of dots are drawn from a narrower or wider range, showing that the mapping of true numerosities into estimated numerosities also shift both the bias and the variability of those estimates. This is the variability of people's estimates for exactly the same number of clouds of dots. Their estimates are more variable when those stimuli are drawn from a wider range of numbers, less variable when they're drawn from a narrower range of numbers. And the biases also, these are the biases. The biases also shift these increasing concave functions, mapping true numerosity into average estimates, are different. The steepness of the bias is greatest when the range of numbers presented is smaller. It becomes less when the range of numbers presented is wider. And Arthur and I have developed a quantitative model of endogenous determination of precision of number representation that can explain these figures in the numerosity context, and that also does quite well at explaining the nature of the shifts in the psychometric functions in the Friedman and Jen data, which seems to begin to think that this basic approach is. So just to wrap up, I would argue subject choices with regard to simple gambles seem to depend only imprecisely on the exact financial terms that are being offered to the decision maker on a given trial. The structure of this imprecision looks to me like it has a lot in common with imprecision in number processing that we observe in other contexts, in particular, the place where it's been studied the most extensively, what we know about judgments about the numerosity of visual arrays. To me, this suggests that the same semantic representation of the size of numbers in the brain, perhaps this representation that can be located in the intraparietal sulcus, is evidently being drawn upon in both cases, both to make estimates of numerosity and to make decisions about gambles. I think that understanding the reasons for errors in choice and what the source might be of people's apparent risk attitudes offers us the prospect of a better understanding of which aspects of observed behavior we should or should not expect to remain invariant across contexts. So what I was showing was that it seems that these psychometric functions describing choices do shift across contexts in response to things that don't involve changes in the actual financial terms or the gambles people are being presented with. I think economists should be interested in understanding that if they want to be able to improve their ability to predict behavior under novel circumstances from behavior that's been observed under some particular circumstances. And this thing has stopped being willing to move, but anyway, the final line is supposed to say, therefore, I think economists need to read more psychology.
Yeah.
Thanks.